Hello students, I am Gurpreet Kaur from Chemistry Department of GG and Khalsa College. Today's video is in continuation with my lecture on delocalized chemical bonding. So, coming to the types of delocalization, there are four types of delocalization. First one is delocalization by pi-pi overlap, in which one pi orbital overlaps with another pi orbital, but the condition is that they must be conjugated. So, two pi bonds must be conjugated, or more than two bonds may be present. Second is the delocalization by pi-p overlap, in which one pi orbital overlaps with the p orbital. This p orbital may be empty, or it may contain one electron or pair of electrons. Third one is delocalization by sigma pi overlap, in which sigma orbital overlaps with the pi orbital. Fourth one is delocalization by sigma p overlap, that is sigma orbital overlaps with the p orbital. The first two delocalization, they give rise to conjugation by overlap, but the third and fourth give rise to hyperconjugation, and I will explain them one by one. So first type of delocalization is delocalization by pi-pi overlap. I will be taking it by taking the example of 1,3-butadiene. So as we know that each carbon atom present here is sp2 hybridized, so there must be one unhybridized p orbital over each carbon atom, which will overlap, which will sideways overlap to form this pi bond. We can represent this pi bond by these orbitals by representing here sideways overlaps. So this orbital can be represented. So these orbitals can be further represented by pi orbital. This is the pi orbital form. This case by side overlap, pi orbital is formed. Now this pi orbital will overlap with this pi orbital, and the condition is they must be in conjugation with each other. So we can also represent it by this way, by showing the delocalization over all the carbon atoms. So the electrons are distributed over all the carbon atoms. Second example I will take of benzene. In this case also, each carbon atom is sp2 hybridized, and it contains, each carbon contains one unhybridized p orbital. So in this case, I will overlap these orbitals, and all these orbitals are planar. And the condition of resonance is that the planarity should be there for resonance to take place. So the structure formed here is this one. This is the equilibrium structure. Then I will overlap these orbitals, these side orbitals. So we got this structure. Then these orbitals are overlapped to form D-bar structure. The last three are D-bar structures, and first two are K-clay structure. So we can draw here the combination of all these canonical structures, which is known as resonance hierarchy. In which all these orbitals overlap and electrons are distributed over all the carbon atoms encompassing all the carbon atoms, which give rise to delocalization, and it can be represented by these pictures. So the electron cloud is above the plane and as well as below the plane. Now moving on to second delocalization, that is delocalization by pi orbital. So I am taking the example of allyl system. And this carbon contains here one unhybridized pair. And this pi bond can be represented by pi orbitals. Another side will overlap of these pairs. So this is pi orbital and this is p orbital. So this pi orbital will overlap with this p orbital. This orbital can contain one electron in case of allyl radical, or it may contain pair of electrons in case of allyl carbanion, or it may be empty in case of carbon-cation. So, taking this orbital empty. So this orbital overlap with this orbital. So these electrons, these two electrons, these two pi electrons, they are delocalized over all the three carbon atoms here. In the case of allyl carbon. In case of radical, allyl radical, these three electrons are delocalized over these three carbon atoms. And in case of allyl carbon anion, so here these four electrons are delocalized and encompassing all the three carbon atoms. So I am explaining the delocalization of sigma pi and sigma p overlap together. As we have discussed previously, that the sigma pi and sigma p overlap leads to hyperconjugations. So in hyperconjugations, the alkyl substituents which contain the sigma orbitals or sigma bonds, they act as a donor of electrons to the pi orbitals. So there are two conditions of hyperconjugation. The first condition is the compound should have sp2 hybrid carbons of alkene, arene, carbon, or free radical. So we are taking these examples and we will find the sp2 hybridized carbon here. So in this case we have this one is sp2 hybridized carbon of alkene. This one is sp2 of alkene. This is also of sp2 of alkene. This is the sp2 of arene system. In this case this is sp2 of carbon. sp2 hybridized p orbital is empty as it is denoted by positive sign. In this case, this is the sp2 hybridized orbital of radical. This is the sp2 hybridized orbital of radical. Coming to the second condition, this. So the carbon alpha 2 sp2 hybridized carbon is this one, and it contains 3 hydrogen atoms. So hyperconjugation is possible, and the alpha position of this one is this. So we have 1 alpha hydrogen atom. Here we have no hydrogen atom, so hyperconjugation is not possible in this case. In this case, alpha to this is this one, this carbon, which contains 2 hydrogen atoms, so hyperconjugation is possible. And alpha to this is this, so we have 3 alpha hydrogens. In this case, we have 9 alpha hydrogens. In this case, we have 3 alpha hydrogen, and in this case, we have 6 alpha hydrogen atoms. So first, I am taking the sigma pi hyperconjugation. So in this case, this is the sigma bond, this is sigma orbital, and this one is pi orbital. So these overlap, which give rise to hyperconjugation or delocalization. I am taking the example of protein to represent the resonating structure which leads to hyperconjugation. So I am taking the example of protein. So this one is sigma bond here, which will bring the electrons towards the pi, and we will get a resonating structure. So here we can see that there is no bond between the carbon and hydrogen. So this hyperconjugation is also known as no bond resonance. But actually there is some ionic character between C and H. And this hydrogen is not free. Now I will use this bond, this sigma bond, as a donor. Now I will use this as a donor. So as we are seeing that there are 4 resonating structures over 3 alpha hydrogen atoms. So this means that the number of resonating